This is Dr. Wood with Citadel Civil Engineering, and this is CIVL 203 Dynamics. And in this brief lecture, we're going to discuss multi-part systems. So most of the systems that we'll work with, particularly for my mechanical engineering students, are going to be made up of multiple pieces. And so when we think about these multiple pieces, these complex systems, and we're using equations of motion, what we're going to have to do is we're going to have to evaluate the equations of motion. So that means both a free body diagram and a kinetic diagram for each part of the system. And so the idea is that if we have a series of pieces that are interconnected, we'll need to break those pieces apart. And when we break those pieces apart, we'll do a free body diagram and a kinetic diagram for each. Now, of course, this is going to expose our common internal forces. And when we're thinking about these common internal forces, typically we're talking about like ropes, right? So we'd have a rope connecting a series of pulleys. We do equations of motion for each mass on the pulley, maybe even for the pulley itself if we're considering it to have mass, and it would have a mass moment of inertia associated with it. But the tension force inside those ropes is going to need to show up on each diagram because we're going to have those common internal forces. We can, in fact, take it a step farther and look at like rigid body connections. So in our example where we said, let's say you wanted to design a bicycle. Well, what you would do is you would do all the kinematics for the whole body, looking at the motion, and then you could actually like cut the member and expose those internal forces, cut the bike in half, or the part of that frame in half, and you would have both tension, normal force, tension or compression, shear forces, and bending moments acting in those planes. And so when you do that, you do the free body diagram for one side or the other, along with its kinetic diagram with a new inertial term at the center of mass in each case for each part. And then you could solve for those internal forces. So those are all sorts of options that we could have to look into doing these things. It's fairly complicated. In this class, we're gonna just stick with probably like pulley systems, and that's the example we'll do. But we'll have common internal forces. The other thing for us to keep in mind is that the kinematic relationships establish our constraints. So when we work a multi-part system like this, we're going to have to remember that this is actually constrained motion. Those places where we cut it apart or pull pins or cut ropes to get all the different pieces with their free body diagrams and kinetic diagrams, that's all great. But each one of those locations is going to have some sort of dependent motion equation associated with it, a common velocity, a common tangential acceleration, or maybe if it's like a pin or a fixed connection, you're going to have common total acceleration. And so the net result of all of that is that these things all work together. And that's what we're really looking for, is that you get those kinematic relationships that establish the constraints as we go forward. So again, multi-part system, we'll break it apart. We'll evaluate our equations of motion with a free body diagram and a kinetic diagram for each part, looking at the center of gravity for each part. We'll have to take into consideration the internal forces that we expose when we break it apart and the external constraints of those common kinematic relationships at the locations where we pulled the system apart. And then we'll be able to analyze the system that way. So that's multi-part systems, and I look forward to working an example problem with you. Thanks.